In this tutorial, we're going to look at interference. So there are two types of interference that we want to deal with in Year 12 Physics. The first one is constructive interference, and the second one is destructive interference. Now, constructive interference occurs when you have two waves and they meet in phase. Okay, so we take wave 1 and we have wave 2 and they meet in phase. So they cross each other in the same place, same time, same wavelength, all that kind of stuff. Okay, so they meet in phase as shown by the diagram. Now what tends to happen is if they do meet in phase, then they superimpose and they kind of combine, they add together. So if we take this one here, wave 1, and we add it to wave 2, we get a third wave which interferes constructively to have a much larger amplitude. Now, to make this correct, if this had an amplitude of, say, 1, and this had an amplitude of 1 as well, then the amplitude of the resultant wave would be 2. So when two waves meet in phase, then they will constructively interfere, and the result will be a wave that is larger in amplitude than the original wave. Now the opposite is also true. If we have two waves and they meet exactly out of phase by half a cycle, in other words, you have the first wave here and that meets a second wave here. When these two meet, they are going to superimpose, but they are going to result in a wave that looks like this. In other words, they completely cancel out. What's happening here is we're having the crest of one wave meeting the trough of another wave. And at this point here, we have the trough of the first wave meeting the crest of the second wave. Now when crest meets trough or trough meets crest, then they will interfere destructively to form a line like this, a wave where there's no vibration. Now of course that's only true if the amplitude of each of these waves is the same. If this was amplitude 2 and that was amplitude 2, then the resultant wave would have amplitude 0. However, if one was amplitude, say, 3 and one was amplitude 2, the resultant wave would be at amplitude 1. So complete destructive interference would occur when the amplitudes of the interfering waves are the same, giving you a resultant wave with absolutely 0. Going back to constructive interference happens when crest meets crest or trough meets trough. Okay, so in an NCEA exam question, you're going to have to put these ideas together to answer a more complicated question. And that is to do with interference patterns and how they work. So I want you to imagine that we've got two speakers. Here's speaker 1 and here's speaker 2. And you are over here. And you're walking in a path across the front of the two speakers. Now a typical exam question will say that as the person walks along the front of these two speakers, what will they hear? Let's assume that the two speakers are playing equal frequencies, okay, and you're walking in front of them. What will you hear? Well, the answer is you will hear the volume go up and down as you walk across or in front of these two speakers. So how do we explain what's going on here? Well, this is quite tricky to draw, but I'll give it a go anyway and we'll see what happens. If we have a look at this, each speaker is generating sound waves. So we've got sound waves from the first speaker, and we have sound waves from the second speaker. And what's going to happen is there are going to be all kinds of positions where the two waves are going to cross and interfere. Now, on my diagram, the blue waves represent the crests. And what I'm going to do is I'm going to draw green waves in between. and those green ones, or the green lines I should say, are going to represent the troughs. So it's kind of a bird's eye view. Blue crests and green troughs. Let's try that one again. Okay, as you can see, we have got areas where blue meets blue. So here, that would be crest, crest, and green meets green here, trough, trough, crest, crest, trough, trough, crest, crest. That there is an area where we have constructive interference happening, okay, where either crest meets crest or trough meets trough. In other words, this is happening, constructive interference. If we join them all together in a line, all the areas where we have constructive interference, we call this an antinodal line. Okay, an antinodal line. An antinodal line is an area of maximum vibration where constructive interference is happening. So it's an antinodal line. Now that corresponds to an area, if you were standing here and listening, there'd be an area where it would be loud. Now, to explain an area where it's going to be soft or quiet or maybe no sound at all in perfect conditions, we look at different areas. So here, where we've got blue meeting green. These areas here where blue meets green, they are areas where crest is meeting trough. If we come back up here, we can see that when crest meets trough, when they're out of phase by half a cycle, that is an example of destructive interference. So if we join these together, these areas of destructive interference, if you were to stand anywhere on this line and listen, this will be an area where it would be quiet, and this is called a nodal line, an area where there's no or very little vibration. Or no vibration. So we have an antinodal line, which means anywhere along that line it'd be loud, an area of constructive interference, an area where the waves meet in phase, an area where it's going to be loud, and we have nodal lines, which are areas of destructive interference, and they are areas where the waves meet out of phase by half a cycle, and they are therefore areas where it's quiet. And of course, across this whole area, you're going to have nodal and antinodal lines all the way across, just going to represent areas of loudness and quietness. Now of course this could be done with light as well. If we had a red laser and we shone it through a diffraction grating and made the waves split up into a similar pattern like the one above, we would have areas again where crest meets crest and trough meets trough, and then also where crest meets trough, and that would be in the areas where crest meets crest or trough meets trough, constructive interference, where you'd see a bright spot, and areas where crest meets trough would be destructive interference, which would be areas where it was dark. Now to give you an idea of sort of how this works in a bit more detail, and this is quite important for excellence, let's look at it in a slightly different way. Let's imagine that we've got our two sources, source 1 and source 2. These can be our speakers. Okay, and over here we have an area where it's loud, so an antinodal line if it was sound, or a bright spot if it was light. Now to describe why that is a bright spot can be explained visually. If we take this, we've got a wave generated by the first source, and it hits at that point there. This wave, if you have a look at it, has to travel further to get to the same spot. Now if it's an area of constructive interference, and I've tried my best to do this, then this wave, the wave from S2, for that to be constructive, has to travel a whole number of wavelengths further. In other words, if the wave from S2, from source 2, from speaker 2 say, travels one wavelength further than the speaker 1, then they'll meet in phase. If it travels 2 wavelengths further, it will meet in phase. So for any situation where they meet and they're out of phase by, sorry, they're in phase, that means that one of the waves has to have travelled further by a whole number of wavelengths. If this one here was a difference of 1 wavelength, then the second antinodal point, so a point here where again the next point where it's going to be loud, that means that the source 2 must have travelled a distance of 2 wavelengths further, for example. We can also explain the destructive interference situation the same way. So if we take a destructive point on this side, say, so a point where it's a node, where it's quiet, and we draw our waves. From source 2 this time, we have our wave coming along, and it's hitting at that point, and for source 1, the wave comes along. It's got to travel further, but this time it's got to interfere destructively, so therefore it travels further by half a wavelength. Okay, so if the wave from source 1 travels further by half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, in each case it'll be a situation where the 2 waves are going to meet out of phase by half a cycle, which means that trough and crest will line up, crest and trough will line up, and it will be an area of destructive interference. On the other side, the antinodal lines or antinodes where it's going to be loud or constructive interference, this is a situation where either the wave travels 1 wavelength further, or 2 wavelengths further, or 3 wavelengths further, in other words, n wavelengths further. That'll be a situation where our 2 waves are going to meet in phase, exactly in phase, where crest meets crest and trough meets trough. That's an area of constructive interference. And this idea of path difference, okay, the path difference being the difference in how much further one wave has travelled than the other, is fundamental to achieving excellence when describing this phenomena of interference.